All right. So anytime you're answering these, the answer to a limit is always this is a value that belongs to a y coordinate. Value of a y coordinate. Doesn't matter what the limit is, okay? This number represents a y coordinate. All right, so what this is telling you is that the y coordinate is approaching, when I see this is telling me the y coordinate is approaching infinity as x gets really close to 0. So this whole limit, all this notation just means as x gets close to 0 from the right, so that means I'm over here on the right and I'm moving towards 0. Okay, that's what this notation means right here. This arrow with a 0 and a plus. I'm moving towards x equals 0. As I'm doing that, the y coordinate is going to infinity. That's what this means right here. So the one on the right means if I'm approaching 0 from the left, so that's here in purple. I'm coming in towards 0 from the left, so I'd be on this branch, and as I get close to 0, my y coordinate goes to negative infinity. Now, when that happens on a graph, there's something there that's making that happen. That's bending that graph like that, and that thing is a vertical asymptote. And in this case, the y-axis is the vertical asymptote. Or x equals 0 is the vertical asymptote. All right, so when we looked at these are, when I say x is going to infinity, okay, now I'm moving like this. If you watch up on the screen, I'm here and I'm going to move towards infinity. That's what that means right there. So as I do that, I can see that the y coordinate is moving towards 0. It's getting really, really close to the line y. This is the line y equals 0. So when I write 0 plus on this means the y is getting close to 0 from above it. Okay, it's approaching the line y equals 0 from above. That's what this means. So this 0 plus, guys, you see it's got two meanings depending on where you use it. Yes. Oh, I need you know what? I gotta have somebody do a chat monitor. Somebody pay attention. I never know. Yeah, I'll do that. Son of a gun. Yeah. Anybody's, jeez. Anybody, sorry, guys at home. Can't see the screen, huh? Okay. Present now. I know they're all just sitting there. Sorry, guys. Forgot to show my share my screen. Okay. Okay, back to this. I'm going to go over limit stuff, you people here at in real life or in class. Okay, so For you guys at home, I was just talking about how to read these limits. And so when you see this notation, you understand what it's talking about. All right, so this little, the X with the arrow on it tells you the direction that you're moving on the graph. So if I see X with an arrow and a 0 with a plus, okay, that represents that I'm on this branch of the graph, okay, and I'm moving towards X equals 0. Okay, so here's the line X equals 0, this vertical line. So as X approaches 0, I'm moving this direction on the graph. That's X approaches 0, the line X equals 0 from the right, because I'm on the right side of it. All right. This one, when you have X approaches 0 from the left, okay, that would represent me moving this direction. So now I'm over here, and I'm on the left, and I'm moving towards 0. So that's what X 0 with a little negative sign represents. Okay, now so this is the direction that you're moving. Okay, and then this is what the y coordinate is doing. Or what does the y coordinate do when you move that way? Okay, so on this one, when the X moves towards 0 from the right, the graph shoots up. So the y coordinate is going up to infinity. Over here, as I move into 0 from the left, the y coordinate shoots down. So I say y is going towards negative infinity. So when you're answering a limit question, these are y coordinates. This is what the y coordinate is doing when the x coordinate is moving in a particular direction. Right? And when that happens, when you get infinity and infinity, that means there's something invisible right here that's making the graph bend. And that what that invisible line is a vertical asymptote. And it would have an equation x equals whatever this coordinate is. In this case, x equals 0. All right, now down here on this one, now your x is going, instead of going towards 0, it's going towards infinity. So this first one, I'd be here moving away from the origin. The second one, I'd be moving away from the origin, but in the negative direction. Okay, that's what those two are telling you. Right? The other two, this is telling you what the y coordinates do. So as x goes way out to the right, the y coordinate goes down. It gets really, really close to 0. Now you see that 0's got a plus on it. So y approaches 0 with a plus. That means 0 from above. See, up here, this meant 0 or x is moving in from the right. So these things have two different meanings depending on, are they associated with an x or a y? Okay. Now this one, when you move out, when x goes way out to the left, the y value gets really close to 0, gets closer and closer and closer, but it's below 0. So we write it like this. So this means it approaches 0 from below. That's what that little negative means there. In this case, and this is above. On this one, the negative and the positive mean right and left. Any questions on that? That's something you haven't seen before. But as we go through this, calculus class, the first things you learn about are called limits. It's values that a limit is a y value that y approaches but never reaches. That's why it's called a limit, because you never get there. Okay. Any questions on this notation? Because this is something that's new. All right. Okay, so the next thing we're going to look at is what does this parameter do to the equation? So what I mean by that is okay. So if I had a reciprocal function, y equals some number over x. Okay, now right now, if we know that this number is positive, okay, we know that the graph's going to be in the first and in the third. Okay, if k is negative, then we know that the graphs are going to be in the second and the fourth. Okay, now what we're going to figure out next is how does a graph, let's say like 6 over x, compare to 12 over x? Okay, how would you tell those two graphs apart? So if I had a blue graph here and a black graph, which one do you think would be the 6 over x and which one would be the 12 over x? How do you tell the difference between these two? Okay, so it all has to do with how curved they are. You're going to hear me say the word corners. Okay, this is the corner of the graph. So the corners, where the corners are, changes. So one graph, the second graph I drew, its corner is farther from the origin than the first graph. So which one would be closer to the origin, do you think? The 6x or the 12x? What do you think? The 6x, and why do you say that? Because it's smaller, closer to 0, okay? Any others? 1, 2, 3. Let's make these numbers a little smaller so it doesn't take so long to graph. So like if this was 6 and this one was 2. All right, how do I graph 6 over x? What points would I put up there? Yeah, so 1, 6, and 6, 1, 2, 3, 3, 2. Okay, so it would look something like that. And then it'd have another side down here. It'd be another one. Okay, now if I graphed 2x, 2 over x. Well, I changed it because I didn't want to graph, I didn't want to have to make 12 tick marks. So 1 and 2, 1, 2, 2, 1. I need some more points. So what are some other numbers that make 2? 4 and what? No, not 4 and, remember these numbers, you got 1, 2, yeah, there you go. 2, 1, but you could use 4, 4 and a half. 4 times 1/2 is 2. 1 times 2, 2 times 1, 4 times a half, and a half times 4. Those all equal 2. Okay, so a half and 4, and then 4 and 1/2. So you can see that this graph is tighter to the origin than 6x. So the bigger this number gets, the further away from the origin that this gets. And the reason why is all this is a vertical stretch. We're taking this graph and we're stretching it by a factor of 6. So in this graph, the point on the graph would be 1, 1, but after you stretch it, it would be 1, 6. Okay, if I took 1, 1 and I stretched it on the 2x graph, all it's going to do is go to 1, 2. This one's getting stretched more, and that's why it appears to be farther away. All right, so knowing that, we should be able to wrap this up here. So we did the limits. All right. Should be on 11. All right, so all 11 was, you were answering one of these two, you were checking which one of these is true. All right, so this, when I move this around, this is the line y or kx right here. And then the blue is the corresponding reciprocal function that belongs to it. So for example, if I put the red dot right there, what's the equation on my, what's the equation of that red line? If I said write the equation of that red line, what is it? This would be y equals x, okay? The x coordinate here is, snip, screen snip. Okay. So if you look at what I had there, the slope of this line right now is 1 up, 1 right, 1 up, 1 right, 1 up, 1 right. So y equals mx plus b. M is 1, b is the y-intercept, so that's the equation y equals x. So then the blue graph is the graph 1 over x. All right. So if I took this slope and made it steeper, okay, by dragging, just making the graph, making this line steeper, then what's that do to the, when when I make this steeper, what's it doing to the blue graph? Or when I make it shallower, what's it doing to the blue graph? Yeah, exactly. Changes the distance from the origin. Now, look at the blue graph. Here's the mother blue graph, okay? That's the blue graph 1 over x. Now, when I make this steeper, am I vertically stretching the blue graph or vertically squeezing it? Yeah. So this movement right here, if you watch the blue graph is getting vertically squeezed. When I make the slope of this shallower, the blue graph is getting vertically stretched. So this would be a vertical stretch, and this would be a vertical squeeze. The corners are getting closer to the origin. All right, so then you're asked to check all that applies here. Okay, so anything that's true, as the slope of the line gets steeper, the corners of the reciprocal function move towards the origin. True or false? True. If I make this steeper, I'm squeezing that towards the origin. That would be true. As the slope of the line gets steeper, the corners move away from the origin. No, that's not true. They move towards the origin, so that one's false. As the slope of the line gets shallower, the corners move towards the origin. So as I make this shallower, no, that's not true. It moves away from the origin. Okay, so that's false. Okay, as the slope of the line gets shallower, the corners of the reciprocal function move away from the origin. True. Okay, if the slope of the line is positive, then the reciprocal function is in 2 and 4. Okay, so positive slope, negative slope. So I can see when my slope's positive, all of these are positive slopes. My graph lives in 1 and 3, and as soon as I make the slope negative, my graphs live in 1 and 4, or 2 and 4. Now I got negative slope. Okay, so if the slope of the line is negative, the graph is in 2 and 4, and if it's positive, it's in 1 and 3. Okay, and there are your true statements. Okay, now the last one, or next to the last one, what you're going to do is you're going to take the graphs and you're going to pair them up. So based on the slope of the graph, you're going to pair it up with its reciprocal function. So for example, and you just drag them together and pair up the cards. Okay, so you're going to look at each one of the cards up here, and then you just drag the card and you pair it up with the one that you think it belongs to. And then we'll see how you do. Okay, so if you haven't done that already, go ahead and go to 12 and take the graph and pair it with its reciprocal function. the inverse of a reciprocal. All right, so if you go to the second to last slide, the inverse slide, does this allow us to open a graph? It doesn't.
Oh, well.
No, you should be able to open up the graph.
Yeah, it does.
Okay, that's all right. I can fix it. You guys are terrible. Spent all this time making this. I was real proud of myself.
I'm proud of you.
But yeah, it looks like I still got some learning. Looks like I got some learning to do. Well, I'll just show you what I had on that slide here.
The other way around. After this, I-
Okay, so let's see. Okay, this is what I had up there. Okay, so when we did an inverse, did inverses back in the first quarter. Okay. Yep. So when you were all at home, when to do an inverse, if I take a graph, okay, so there's the graph for y equals 3x plus 4. That's a linear graph. That's a linear function because when you graph it, it's a line. Now, to write the equation for its inverse, all I'm doing is I'm just switching x and y. So if you look at the next one, I swapped x and y to graph its inverse. So where there was a y, I wrote an x. Where there was an x, I wrote a y. So the inverse, if I graph that, that's its inverse. Okay, now the dotted orange line is the line y equals x. And the reason that's on there is because to get the inverse of a graph, you flip it over that line. Okay, so the distance that a point is from the line, so like from this point up here to this dotted line, the distance from this point to that dotted line is the same. So this point right here flips to that point. And you see all that happens? The x and the y switch places. All right, so that's the graph and its inverse. They're different. Okay, so let's unclick those. Now let's look at a quadratic and its inverse. Okay, so here's a quadratic. Now look what I did. I just switched x and y. Now let's graph its inverse. That's what the inverse of a quadratic looks like. All right. Okay, now I'm going to do a cubic function. So here's what a normal cubic function looks like. And when I switch x and y, it looks like that. All right. Okay, now I'm going to do a reciprocal function. And what's its inverse going to look like? You ready? So a reciprocal function is its own inverse. They're the exact same thing. So we call that, it's a self-inverse. So that's what I had on that slide here. So using the previous slide, okay, it said identify which one of these is its own inverse. Okay, the reciprocal function is its own inverse. Yeah, you don't have to turn anything in. Yeah, once you're done, it's recorded. Okay. All right, so if you go back to your note packet, so the big ideas for reciprocal functions. Okay, what we just did was this page right here. So when you did a reciprocal, okay, a reciprocal of a or the inverse of a reciprocal function is itself. It's the exact same thing. It's its own inverse. Okay, so for Monday, do this assignment, and then Monday I'll have your reviews ready uh, for your final. So your final will cover what we did at home, which was all this stuff. This is all the stuff that we did at home for over the first quarter. Then we did all the stuff on functions. So it'll cover like composite functions. It'll cover identity functions and inverse functions. And then the stuff that we just finished, the modeling. So your final will cover these two units, chapter 2 and chapter 3.